Here we are down to protection mechanisms. That's what I'm going to talk about. And then I have a project to demonstrate briefly, and then I really want to demonstrate the machine learning. If you're in my forensics class, I already gave a complete demonstration of this, but I don't think very many students are taking both forensics and 127, and it's so important. I highly encourage every student in all my classes to do these projects, because machine learning is probably more important than any of the content in any of my classes right now. So anyway, let's start with the chapter 14 stuff, which is mitigations. Protection mechanisms to stop the kind of attacks we've been doing in this exploit development course. So, non-executable stack is one of them, also called data execution prevention on Windows. And this principle, either writer or executable memory, but not both. And then stack data protection. There's canaries, ideal layout, ASCII armored address space, and address space layout randomization. We'll talk about all of them. And then heap protections. There's quite a few of these. Microsoft has a lot of fancy ways to limit the harm of heap overflows, and then structured exception handler protections on Windows. And as I just discovered from that article, apparently the world of Linux and Unix has not even begun to consider this attack or how to defend from it, and they're going to have to catch up in that regard. So there are two kinds of protections. There are general protections you can put in, say, the operating system. So if you get a later version of the operating system, it will protect you even if you run old code compiled for an old version. That's nice. Often that is not possible, but that would be nice. And the other alternative, of course, is there are some protection mechanisms where you must recompile the code because it has to be compiled differently to put in the new security measure. And we'll talk about both types. So here's C code with a buffer overflow. You've got a buffer here that's 80 long, and you can pass in an argument of arbitrary length which gets put in the buffer, and therefore there can be an overflow. So in this function, you've got variable 4 bytes, buffer 80 bytes, variable 1 byte. Then you have the saved EBP, which is also called the frame pointer, that points to the start of this stack frame. And then you have the saved return address, which is used to return to the program. And the point of a buffer overflow attack is if you're filling this buffer, if you overflow it a little bit, you change this variable, and that may have unexpected consequences. That's an exploit of sorts. But if you overflow it more, then you change the frame pointer or the return address, and then you can directly control which code is executed and take over the box in a simple way. That's the kind of vulnerability that we have been exploiting and that we want to talk about defenses against. So the simplest one is a non-executable stack. In the simplest case, you would actually inject your code onto the stack and then put in an address that will jump to the code. In this case, if it's only 80 bytes, you'd probably put the code down here and make the return address jump down there. But the point is you would inject code on the stack, and then you would execute it on the stack. That was the original version of the Aleph null exploit. And so one way to prevent that is to mark the stack non-executable. You can put data on the stack, you can write and you can read, but nothing you put there will execute. And this is by default in almost all modern operating systems. And so you can still overwrite the return address, but if you jump into any of the code you've injected, it won't run. So you can still perform a code reuse attack where you jump to some other code that the developer put there, but you're not able to inject your own code. Now, there are other ways to do it. There's return to data, where you put your shellcode in the data section, which is probably executable, and you use buffered IO somehow, put it on a heap or something like that, and then use the corrupted return value to jump to it. So if you can find an executable section you can write to, then you could do that. All right, return to libc will jump directly to code in libc. You can jump to, say, system. So you basically do a operating system level injection. Let me go back to this one. This one here, you're going to have to somehow move data on the heap. So you put it in the data section, and then that may be executable. I'm sort of confused about this write or execute. I'm not quite sure about how that one works. Anyway, return to libc, you jump to a C library. And so, all right, you can inject, call a C library like system to execute a Unix system command. And then you're not injecting code, you're just injecting a command. You're not executing your code, you're just jumping to an address which contains a C library function, and then you're putting parameters on the stack which will run. So you'll call system, and on the parameter you'll put /bin/bash, and then like a netcat command to open a shell. You're not executing that code directly in the program, you're just passing it to a system library as an argument, which will then execute it. Return to string copy is another way where you call the string copy function and you put your code after that as a parameter. So the code is not executed, but the string copy command copies it to another address, and you copy it to an address where you can execute it. So you copy it somewhere, and this overcomes two flaws. You can copy it to a segment with execute permissions, so you can run it, and also you can copy it to an address you know, so you defeat address space layout randomization, because you know where you copied it to. So here's ret to stir copy. So you inject stuff, and what you do, instead of trying to inject a return address that would jump to your code, you put in, you jump to string copy here, and then you put your the address you want to write to, and you put your code down here. So it will call string copy, and it will copy from this location to that location, and you put your exploit down here somewhere, so you control where it's going. All right. Then there's return to Getch. This is very simple. You jump to the call Getch. Now it will read data from the keyboard, from the standard input, and you can just type in code which will turn into your exploit, and then it will run. So that's a simple way to do the same thing as string copy. You get to feed in data that is just treated as data, but then it gets copied somewhere where you know where it is and where you can execute it. All right, so here's return to Getch, the same thing. All right, you put the Getch pointer there. Then there's return to code. This is the general way of code reuse, like I've been saying, where you jump to some code that's already there. Something in a library, something. It can be any code or fragments of code that you can reach if you can find the address for it. And we've used this in the projects in Windows where you had to find one library that was not using address-based layout randomization, so you could jump there to find a trampoline. We did that for the structured exception handling attack. And you can use chained ret2 code, where you just do a series of calls to existing code. You get a few instructions here, a few instructions there, and you sort of build your exploit out of it. These are called a trampoline, and in a longer expression, it's called return-oriented programming, where you build a program out of little fragments you find. All right. Return to syscall will you find two code fragments to put together. First, you pop the arguments into registers, then you issue a syscall. So now you can make a direct syscall to a kernel module that will do something. And that's another way to do essentially the same thing. Then there's return to text. You jump into the text section of the binary where the program's code lived, and this is what we've done before when there was a winner function, and you had to just jump to that winner function. The text section is where the compiled code written by the developer is, and you just use that. And I say this will defeat these protections entirely. Address-based layout randomization will not be defeated. Well, you're going to have to somehow find the location of the text code, so that may be a problem, but write or execute will not save you because this code is clearly executable. And you're not writing to it, you're just using code that the developer put there. Then there's a jump to the procedure linkage table, which we've used in these exploits, where you find a table which points to system routines like exit or print, and you can jump to this linkage table, and that will go to the functions called by the program, so you can make an unexpected call to a library function that the program calls, so you're going to jump to that call with parameters of your choice and execute whatever code is there. Then there's one where you jump to the dynamic linker resolver that can load libraries dynamically. So in this case, you can jump to, if you can find this and jump to it, you can request loading another library that the developer did not load at runtime, which is pretty nice. All right, so non-executable stack. You can write to it and read, but you can't execute it, but you can still put addresses in there. So that's the problem. You can do this thing called return-oriented programming, which is what all this is, where I don't inject code, I just inject addresses to code, and those addresses are used to execute series of little pieces of code. So I still can take over the box, even though I was not able to directly inject executable code. All right. And so we'll do this in hands-on project later, but you can watch these defenses. You can put a label in the text section here. You can put inline assembly. So this is going to define a label. And the label is, up here is int D is in the data section. And I move label to EDX and EDX to D, and label not. I'm not quite understanding what this does here. Oh, here, in assembly code, I define a label. This is going to be in a data section, and I put something there like a Mmap. So it's defined. This puts it in EDX and puts EDX into D, so now I can print out the value D. So this is just a way to print an address in the text section. There's a label here. All right, then I'll do a program later where we make a C program to print out some various addresses so you can see which segments are randomized. We're going to do that. So here's how you get something in the data section. You print out a pointer to D, and here's an address on the stack, and here's an address in the heap. So we're going to use this program later. You'll see it just prints out a series of addresses in each code section so you can see if they're randomized or not. And then you just run it, compile it with protections, and now it will print out a series of these addresses and print out the stack, and you can then run it a series of times to see which things change. We're going to do this later. All right, you can do it with and without ASLR and see what changes. And one thing you'll see is the stack cookie here will change every time you run it because, of course, that's a random value. So this is the stack. These are the parameters used by the subroutine. Here's the return values, and the cookie appears before the return values, and it's a random number that's hard to predict. So if you were to overflow one of these variables and try to get to the pointers, you would corrupt that, and the operating system would detect that and stop you from doing the exploit. All right, let's try a Kahoot, which is 14A. All right. Owls today. No more food. Okay. All right. This may be everybody. All right, so what method puts shellcode on the stack but executes it in a different memory segment? String copy. You put the data on the stack where you cannot execute it. You use string copy to copy it somewhere where you can execute it, and then execute it there. All right. Right, which defense stops code on the stack from running? NX, the non-executable bit. That's what it does. It's, all right. I'm sort of troubled that not more people didn't get that. We've been talking about that all along. NX marks areas of memory non-executable, and that's what's used for the stack. All right, which method jumps directly to system? That's return to lib.c. That's a system library. Good, all right. That's a system library call. All right. And which attack reads shellcode from the standard input? Yeah, going to Getch. Getch reads from standard input. Okay, so the winners are faces, okay. Honey. Good. And V. Good. So let's go on to the next bit here. All right, so I mentioned write or execute. This is a rule, no so you should have either write or execute permissions, not both. Therefore, any place you can put data will not run. NX was confusing. Well, yeah, apparently I didn't think it was, but that's the point. NX is the simple way. A non-executable stack means you can read and write to the stack, but you can't execute. Since you can write, you're not allowed to execute. All right. So an early Linux implementation of this was called PAX. It was considered very secure, but it seemed to slow it down too much, so it's never used by any modern distributions. Wasn't considered practical enough. The NX bit is what we have now in Windows XP and all later versions of Windows. They call it data execution prevention. In client versions of Windows, like Windows 10 and Windows 11, it is opt-in, which means this is only applied to essential system processes. On servers, it's applied to everything except things you add to an exception list, which is why, because for client versions, you probably want to run old code that's written sloppily, that relies upon writing and executing code. But on a server, you probably only want to use modern code that doesn't use this poor practice. Anyway, so write or execute, even if you enforce this, where no memory region has both write and execute permissions, you can still use return to code, like we said, where you just jump into code that's already there without changing it. So you find an area that's executable, but it's not writable, but you can still do it. Return to code will work. And some memory sections may still allow writing and executing. You can use chained write to code to write to the disk and define a new memory region that permits this and then go there, for example. The operating system doesn't totally prohibit this. It is possible, it's just that it's not used in the normal course of events. For F220, I don't have Internet Explorer. Yes, I think you'll find you don't need Internet Explorer. Just skip over the part, and you don't need it for the flags, because I'm aware of that. Internet Explorer is pretty much over. All right. So you can also turn the protection off. There's a library call, set information process, that will turn it off if you can eject null bytes, which you often can't. And you can change a specific memory region with virtual protect. You can just turn off this protection by calling a Windows API call. So that's an issue. If you can execute a API call to turn it off, then it's off. So, all right. Then there's X after W. This is another way to do it. First, you make it writable and write. Then you change it to executable, non-writable, and write it. So you accomplish the same thing. You write to it and then execute it later. You can also, as mentioned before, you just create a new region of memory that permits both of these. And this is possible in almost anything. You can use virtual alloc in Windows or Mmap in Linux to create a new memory region, to allocate a new memory region. All right. And to protect data on the stack, there are various kinds of canaries, which are these values placed to detect if you overrun the buffers and you're hitting the return pointer. Stack guard was first. Pro Police was the improved version. This is what you see in GCC. This is what you'll see, an error stack smashing detected when you have a buffer overflow on modern versions of Linux. Stack guard only protected the return address, but not the base pointer. And it turns out that this base pointer, you can use that to control code execution too. So this was considered not a very strong defense. So they replaced it by Pro Police and Visual Studio's protection called with /GS. And so that puts the canary where it protects both the EBP and the return address. And then the issue is, what value should you use for canary? one of the first things people tried was a null canary, where it's all nulls, assuming you won't be able to inject those nulls, but there are ways to do it, so that wasn't considered too good. Then they made a terminator canary, which had a null, then a carriage return, a line feed, a carriage return, and an FF, which is an end of form character, figuring that each of these will end any kind of input. And so if you try to write a buffer overflow exploit that injects this stuff, one of them will terminate it. That was the idea. But even that was considered not the best answer. The best answer is considered to be use a random canary. All right, so then there's also ideal stack layout. Remember, there's still an attack where I leak out of one variable into another variable and I don't hit the canary. And the canary does not prevent that. So to prevent this kind of attack, where you leak from one variable into another, you can use an ideal stack layout. And what this does is it puts the buffers at the end of the stack, so they won't overrun into other variables. And so you take the non-string variables and put them first, then you put the buffers at the end, so the most you could possibly have is one buffer leaking into another buffer. But you can't get anywhere hitting the canary. You just put it down here near the canary, so it's likely to have less overflows for you to exploit. That's the ideal stack layout.
Random canary,
yeah.
Keep track, right?
Yes, when you enter the program, it calls a function to prepare the canary. Then it goes and loads a random canary which generates using something like a clock and other things, and it saves it in another memory segment and writes it here. And then when you exit,
each time you start up, it's not random every time.
It's every time you enter the function, it creates a new random canary and saves it.
But that way you have to have a big space to keep track of all those random.
No, it only needs to remember it, and that's right. It puts it in another memory segment. That's right. It has to have enough to remember a canary for each function you've entered. And that's why, at least in the Microsoft implementation, it doesn't apply to every function call. It only does it if your function call has a string, which is more than 10 characters, I think. So it decides whether it looks like an overflow is possible. And if that's true, then it makes a canary, and you're right, it will have to remember them all. When you return, it can forget them. But if you call a function, and that calls another function, and that calls another function, you would have to remember all three canaries, and it does that. It takes another data section and keeps track of them all.
They seem a lot of bookkeeping.
Well, that's right, and that's why it's considered expensive, and that's why they save processing time by not implementing it on every function call, but just the function calls that appear to have a vulnerable buffer. But you're right, it does add a preamble. More to the preamble when you enter a function, it adds more to executing. So it costs some CPU time. All right, so that's why I say they make compromises for performance. They don't protect every function. Visual Studio only copies vulnerable arguments. It only protects vulnerable arguments. So if a function contains several buffers, one a buffer for an overflow into the next one, and there's no way to prevent that. Even the ideal layout won't prevent it because buffers are followed by other buffers, and the canary won't prevent it. So you could, this one, there isn't any known defense that I know of to stop it. Also, there's other issues. If you define a C data structure that might have parameters and strings, those can't be rearranged. They have to be right in order in memory. All right, so that's an issue. There are certain code structures that cannot be rearranged and cannot be placed in their ideal layout, so it's not a perfect defense. Buffers that are dynamically allocated are always on top of the frame. They can't be moved. And of course, there may be something valuable located after the buffer. In Windows, the exception registration record is stored on the staff. Other variables can be overwritten. So, in principle, overflowing from one variable into another might be dangerous even though you never hit the canary. But this lowers the attack surface. It means there will be less vulnerable spots in your code. And then there's ASCII armored address space. What you do is you load all shared libraries in low memory, starting with null, because now you won't be able to inject any of those addresses. They will contain a null byte. It's a simple way to do it. Of course, it's better on big endian architectures, which is what most of us are using, where the null is at the start of the address. All right. We're using little endian. All right, anyway, that's right. Little endian, you might be all right because you can inject one null at the end of an address. And for little endian architecture, that could be the end. So this may fail if your address is the last bit of your exploit, because you can inject one null. All right. So here's an example. You want to execute this command, which will add a new user account to the system. Somebody named Jira will be added with the ability to, in the password. You can make one call to system by making the last injected byte null. So you have null to terminate the string. Yeah. All right. Anyway, so to defeat this, you have an address here, and you have a payload. Here's the new frame pointer, and here's system after 3. We're going to, here's system, and we put a null byte at the very end. And that can work, even though you're trying to address something that has an address starting with 0, because the last byte, this is a little endian. So the last byte is the most significant byte at the end. So the fact that you have a null in the address doesn't always mean you can't exploit it. Again, it lowers the attack surface, but sometimes exploits will still get through, which is true of all these defenses. All right, and that's the issue. The main executable is not moved there, and there's other things that are not moved to the ASCII armored address space. So it's not a perfect defense, but it does remove some of the exploitable library files. So let's try another one of these. I'll make a note that I should take IE out of F220. You can skip it over, but I should just take it out of the project since IE is gone. All right. All right. All right, I guess we got whoever's coming. All right, so what defense is very secure but not used? Packs. This is very common. Cubes is a very secure operating system, but almost nobody uses it. There's a bunch of things that are secure. There's a bunch of cryptographic techniques that are secure, but they're too hard to use. So packs is one of them. PGP encryption is very secure, but it's so hard to use that even the developers have quit using it. It's quite common that you have a secure thing, but it's not usable enough. All right, which defense places shared code in low memory addresses? All right, that's ASCII armored address space, where the ASCII value null is included in all the addresses, and therefore it's hard to exploit. Which defense protects the return value, but not the EBP, the base pointer or the frame pointer? That was StackGuard, the earlier one, which was replaced later on. All right, and which defense causes code to stop when it hits a NOP, tries to execute a NOP instruction. We did this in the projects. You would test for executability by injecting a series of NOPs, and if the non-executable is turned on, it won't execute them. It will stop on a NOP. Otherwise, it'll run through the NOPs. So the only thing that causes a NOP to not execute is you don't have execute permissions. All right. There's a confusing name. I think that's probably not a real student. Faces is also not a real student. Rouhani is a real student, however, and they'll get points. And this person with a lot of letters will have to tell me who they are if they want their points. All right. Anyway, all right. And then there's address space layout randomization, which we're going to talk about more. Yes, you did. I got you, Rouhani. You used a name I could recognize. All right. So, all right. So, one problem with address space layout randomization is it causes a performance hit, because now you have to use a register to keep track of where you are, and all the addresses are relative to that register. And the problem is, in a 32-bit operating system, there aren't very many registers. So tying up one of them slows down your code. You have to spend more time copying data in and out of the registers. So this causes a performance hit, and therefore it doesn't randomize all the code. Just like the Canary, it is too expensive to implement it all the time, so it tries to guess where the most important place to apply this defense is. So there are ways to defeat it. You can use return to Getch, which we talked about. That will read from the standard input and put it wherever you told it to put it. So you specify the location, and now you can you know where things are, even though there's randomization. There's another thing called linuxgate.so, which is a table of pointers used for system calls, and sometimes it's at a fixed location, so you could read that there and find out where the memory segments are, leaking out the addresses that are randomized. And sometimes the randomization is not strong enough. If there's only 8 bits of entropy, that means there's only 256 possible random values, so you could just run your attack several hundred times until you get lucky. This was happening in Windows XP Service Pack 2. The heap cookies only had 8 bits of randomization. In Windows 7 and Server 2003 and later, there are other defenses to help protect the heap. And also, memory sections may all move together with a fixed relative location, and that would mean you only have to have one guess to get in. That would be, if you move them all differently, independently, randomly, it would be harder to predict. All right, another thing is if you can escalate privileges, you might be able to access the memory map. On Linux machines, it's in the proc folder. Proc process ID maps is the map. So you can just read the location of the memory segments there. Also, even a 16-bit value can be brute forced. That's 65,000 guesses. A 24-bit value, you'd have to run it 16 million times to brute force it. That may be possible, although usually that's impractical. So, a format string exploit. We've seen this before. If you have a format string, you can read the contents of RAM so you can find addresses, like the memory map or other addresses, pointers to things that tell you where the code is. There are remote procedure calls that leak memory addresses in handles that are returned to the client. In multi-threaded Windows applications, the address space must be the same for all the threads, so if you can find a way to leak out the information from any thread, you'll have it for other threads. And fork. Unix processes use fork to copy themselves, and I don't know if this is still true, but at one time every process in Unix was a fork of init. Init was the original process that booted up the operating system, and every other process was a fork from init. And the point is, fork does not re-randomize the memory layout. All right, and then there's heap protections. If you find a way to overflow one chunk into the next chunk, then you'll end up controlling an arbitrary write operation. All right. When you delete a chunk, for example, in other operations, they'll try to fix these pointers, and that will involve writing to an address you control and writing a value you control. We've done those exploits in the projects. So SafeSeh Unlink is something that will check the pointers before freeing a chunk. So before it frees a chunk, it will make sure that the pointer is intact, that I can go to the previous one and back, and I can go to the next one and back. That means the forward and back pointer links are both working before it frees the chunk. So it will prevent the simple kinds of attacks that we did in the projects. It's implemented in glibc and Windows in all modern versions. However, not all heap operations are protected. And there's a thing called the malloc maleficarium, which has all kinds of complicated heap overflows that can defeat modern versions of heaps. Then there's heap exploits on Windows. There's something called unsafe unlinking, where what you do is you overwrite the back and when you do the overflow, you don't just arbitrarily overflow these, you carefully write values so they will pass this test. You changed it to something else, but you make it so it can jump forward and back. You can carefully perform your overflow so you make something that is a good forgery, that will pass the test, and also give you control of the box. All right. That's unsafe unlinking. All right. Then there's chunk on look-aside override. Microsoft has a thing called the look-aside list that keeps track of free chunks so it can defragment the heap for performance purposes. And if you can write there, then you can write some addresses there that will eventually be used to try to, I think, defragment the heap, and it'll involve a write that you can write to. However, Microsoft has changed this in Vista and later, which is all modern versions. Now they use something called a low fragmentation heap instead. And Windows XP used 8-bit random cookie at the end of each chunk header. So it would look for this, just like the stack cookie. But again, it's only 8 bits, so you can just try 256 times to get in by luck. Nowadays, it uses 8 bytes for the cookie. And it has other integrity checks. So this is strong heap protection. It's very difficult to accomplish a heap overflow in modern versions of Windows. And Windows 8 added even more protections, heap handle protections, and guard pages, and exception handler removal, many other new defenses, and these mostly come from Microsoft's Blue Hat program. Back in the days of like Windows XP and Windows 2000, Microsoft thought hackers were evil, and they just thought everybody should just shut up and not advertise our vulnerabilities and everything will be fine. But they finally wised up and realized that you do want the hackers to tell you, so they started inviting people to the Blue Hat conference, where they will pay you $100,000 if you find a flaw in Windows, and they will pay you another $100,000 if you fix it. So the defenses got much better. And there are clever defenses to stop all these attacks now coming from their ethical hacking program. There's more and more defenses here. Safe unlinking in later versions of Windows, safe linking. There's something called a pool cookie in the look-aside chunks and so on. All these things I don't really understand, and all these details. Microsoft heaps are very complicated, and they have a lot of very complicated defenses. All right, even more, there's cookies in the kernel. There's non-executable kernel, and to stop heap spraying, which is an attack I used to have, but it only works on really old versions of Windows, where what you do is you use JavaScript to put thousands of copies of your exploit all over memory, and then you just jump to a random memory location, hoping to hit one. That was possible, but Microsoft has put defenses against it now. And they use much improved randomization. With the modern CPUs, there's a hardware random number generator in the CPU, so you do not have to use an imperfect system like taking a counter or the key presses of the user as something as a source of randomness. There's a real random number generator built in the processor, which should be truly random. And of course, the issue is, how random is it? And some people refuse, like FreeBSD refused to use it, because there were several times when it came out that the government had poisoned cryptography. And so they say, we have no way to audit that random number generator and know if it's really random. It could be producing predictable random numbers, and we would never know. So most people use it, but some people that are suspicious refuse to use the hardware random number generator, like FreeBSD. All right, and there's even more. Windows 10 defenses. I don't think I'll go through them in much detail, but there are many other things. UEFI Secure Boot is a big one. I'm always hearing about on Paul's Security Podcast because he works for a company that is trying to develop more secure firmware defenses. And this prevents bootkits by verifying the code used during the boot up process. And there's more ways to stop rootkits. All right. And in Linux, OpenBSD and FreeBSD, they used to use allocation, but now they switched to Mmap, which is more secure. It has randomly located chunks of RAM using address space layout randomization for the heap, and no two chunks can ever be adjacent, so it's not so easy to overflow one chunk and write the next chunk. And there are heap exploits. It's becoming quite difficult, but sometimes there's something else that the programmer uses, like a data structure where you have a string followed by a pointer that's used. So like I say, this is like the overflow we talked about before, where you overflow from one variable into another variable. That's only going to rarely work, but if the code happens to have that kind of layout or structure, you might have an exploitable thing there. And this, I think, is how our first heap exploit was in the project. We made a data structure that had a string followed by a pointer. So all you had to do was make the string a few bytes longer, and you'd override a pointer that ended up controlling the EIP. And that's nice when it happens, but that will only happen rarely when a programmer makes this unusual construction. All right, and then there's the structured exception handler that we've exploited in the project. So the registers are now zeroed before calling the handler, so it doesn't have address information. The handler can't be placed in the stack anymore. She can't inject code on the stack and jump to it. Portable executable binaries can be compiled with SafeSeh. We had to turn this off in order to do our structured exception handler exploit. This then uses an allow list of permitted exception handlers, so you can't jump into a function anywhere except at the official entry point. So you can't find pop return like we did and make a trampoline. You have to run the whole function or none at all. This greatly decreases the ability to make return-oriented programming exploits. All right. However, if you have code not compiled with SafeSeh, then it won't have that defense, but it may have some other defenses. And so there are tools just to exploit the structured exception handler. EEREAP is one of them. It'll find trampoline code. PDEST will freeze a process and hunt through the RAM to find trampoline code. And SEH Inspector will inspect to tell you if these defenses are in effect. These are just some of the many tools to do it, although we had pretty good luck doing it just with Mona in the immunity debugger. All right. So I know there's a lot of stuff there and you may not remember it all, but it's good to see it. If you see it 2 or 3 times, you remember it better. Those defenses can be pretty confusing. And now something seems to have... Oh, well, I got to turn in my power, I guess. Let me try that. I'm getting weird... I'm getting a strange inability to see my my second screen here. Let's see if plugging in the power makes it happier. No, I think it just means this cable came loose. I can see it on Twitch, but I can't see it in the room anymore. I think it's just this old-fashioned 9-pin RGB connector that they use in this room is just not very reliable. There we go. All right. Now I can run the last Kahoot. All right. Aliens now. All right. So which one of these protects you from heap overflows? Safe Unlink checks to make sure that the pointers appear to be unaltered before unlinking a chunk. All right, what attack bypasses ASLR because you specify where to put the shell code? Exploit to Getch, as we talked about before. All right, which one exploits the structure deception handler? E-reap is intact true. All right. All right, how many guesses will it take to find two independent 8-bit values? $65,000. To find one 8-bit value is 256, but to find two independent ones, you have to square 256, and that gets you 65,000. This is 2 to the 16. All right. So, all right. Spaces. And V. And we have it. Good. All right. So, when we stop the recording,